matter measurement and problem solving, but we're going to start part 3. In the previous ones, we've done properties, identified substances, matter, and we're going to now get into the math part. And as I said in the introduction, chemistry is a two-part class. It's part math, or applied math, and then it's chemistry. So here we're going to start with the math. All right, the first thing we need to talk about is some more definitions, and this is thermodynamics. And in chemical reactions, we're going to transfer energy. And thermodynamics is basically looking at energy. Energy is the capacity to do work, or transfer heat. And if you've taken physics, you've seen this before. Transfer heat. And it's pretty much the same definition. In physics, you kind of concentrate on the capacity to do work. In chemistry, we look at the transfer of heat as more common. And work would be the action of a force, through a distance. Okay, and again, that's more physics based. We're going to look more at the heat transfer, but there are different types of energy. Kinetic energy is the energy of motion. So when things move, mechanical, thermal, electrical is movement of electrons. That is kinetic energy. Potential energy is the energy of position. That's where it's located. So if your feet are on the ground, then you have low potential energy. You climb up to the top of a 30-foot tower, then you have high potential energy because it's stored. Chemical energy is the energy of reaction. So the reactions that take place, and it's stored or transferred within the bonds and changes as you change species. Thermal energy in general is the energy of the random motion of particles, and this is basically the temperature. Radiant energy is not something we really deal with in this course, but it's just fun. It's the energy of the sun. So when they start talking about stuff with respect to solar panels and stuff like that, they're really talking about radiant energy. So these are definitions of energy. Well, what do we do with it? Well, the first thing we do with it is the first law of thermodynamics, which is the law of conservation of energy. Energy cannot be created or destroyed. It can only be converted from one form to another. So when we talk about energy, we say it can't be created or destroyed. You only transfer it. It's only converted between forms. That's between. And I'll use that one a lot, as you'll see it. So when they talk about renewable energy, I always get the giggles. It really should be recycled energy because there's no new energy. You only convert it from one form to the other. Like solar, you convert radiant energy into electrical energy. Wind is energy converted into electrical energy again. So you're converting it. You're not making it new. So when they say renewable, it's like you made it fresh. So it really should be recycled, but okay. Recycled doesn't sound as good as renewed. All right. So when we start talking about these things, we're going to get into the number part. Well, you need to understand that when you get it within the number, there are always two essential parts within the sciences. You have a number, that's your quantitative piece, and you have your unit, which is your qualitative piece. So what's this mean? So if I said the number 60, What's that mean? If we're talking about wages, are you talking about $60 per week or $60 per hour? Which one is preferable? Does it matter? Oh, yes, it matters, because $60 per hour is pretty good. $60 per week is not. And so we not only need to know what the number is, but it's also important that we know what the unit is. The other important thing about the unit is in the sciences, knowing the unit or following your units will tell you where you need to go, which helps you in working the problems. So if you drop the units, you tend to get lost in the numbers. And in order to deal with the units, we have our, again, I told you that chemistry was like a foreign language. Well, we have our metric system of units, and we call this system of International System of Units, or SI units, System International, and it's the French, so we have to revert it. So we're going to use meters, kilograms, or if it's small, we're going to use grams if it's small. And the SI unit for temperature is Kelvin, but we're going to use just degrees C in lab. More about that in a minute. Seconds, that's that same. Moles are really critical for chemistry, and we'll show you how to convert that. But basically, it's a counting number for chemistry. Electric current is an ampere. If you go on to 1212, we will deal with that. Luminous intensity is a candela, and we don't use candelas. It's just fun to say. So there's your basic units, but we're going to use these in a variety more. And the trick is that when we're talking over here with the kilograms, what we're really doing is the kilo is a unit, grams is your basic. Okay, so we're dealing with meters, grams, and liters, and we'll walk through each of those as we go. All right, so here are the common SI prefixes. This is the one out of the text. This is the one I like you to know. And you need to memorize this. See the little orange memorize. Now, don't freak out, because most of these you actually already know. And the other thing is we've got this demarcation here. This is the same on this side as on this side. It's how you look at it. So, for example, here's kind of your baseline start point. Okay? So, if you'll notice, these are bigger and these are smaller. So the thought process is the smaller the unit, the bigger the number. The bigger the unit, the smaller the number. So the way that works is, some of these you know, most of you will know what a kilometer is, because, or kilometer, whichever way you want to pronounce it. Because if you drive a car, then you've seen it on your dashboard. But the other ones like deci, centi, milli are not unusual. What's a decade? 10 years. To a deci is 1 over 10. So if you'll notice, this is 0.1 or 10 to the minus 1 or 1/10, whichever way you want to look at it. Okay, centi, milli. Centi is a century. Milli, millennium is 1,000 years. And then some of them, like micro, are actually not uncommonly seen if you read your drugs or whatever. Nano's easy because it's 9, picos 12, femto 15, etc. Now, I'm using big numbers here, and so if you notice, 1 femtogram is 10 to the minus 15 grams, or you can say that 1 gram is 10 to the 15 femtograms. So the reason why this works is because this is the small unit. So in each case, whether you're dealing here or over here, the small unit gets the bigger number. So femtogram will get the bigger number in both cases. And 1 is bigger than minus 15, and plus 15 is bigger than 1, 10 to the 15th. So the trick is that ideally you need to know these, and the reason is that you're going to use them a lot. And so because you're going to use them a lot, if you go ahead and memorize them, it makes your life a whole lot easier. You don't have to memorize them, but when they appear on the test and you run out of time because you didn't memorize them and you have to think about them, you get in trouble and life's not pretty. So the trick is that if it were me, and I'll go ahead and add a slide here. So if it were me, I would use an index card, and you can do the front and the back, and you can do this a variety of different ways. So I'll pick on nano. So a nano, and it doesn't matter if you're using meters, liters, or grams. So you can say 1 gram is 10 to the ninth. Or actually, in this case, if you're using grams, etc. So 1 nano is 10 to the minus ninth. Or you can say there are 10 to the ninth nanos is equal to 1. Okay? Gram, liter, meter, etc. And again, you just have to know. So, for example, a femtoliter is the unit on that is 15. So 10 to the 15th femtoliters is equal to 1 liter, or 1 femtoliter is equal to 10 to the minus 15th liters. Notice that the smaller unit gets the larger number. So if you always remember that, then it's easy to remember. And I'm not going to lie, I tend to go on half of one side of the chart and the other half, because I tend to remember that there are 1,000 milligrams in 1 gram, as opposed to 1 milligram is 10 to the minus 3 grams. Okay? You can remember them any way you want. Just go with it. Now, the question is why is this important? Well, it's really important when you're starting to work with a variety of numbers, because a lot of times you're working with really big or really small numbers, and it's easier to convert them. So, for example, if you have 2.4 times 10 to the minus 12, and 10 to the minus 12, that means you're really big. So that would be 2.4 teraliters. Okay, is it easier to say teraliters than say I have 2.4 times 10 to the 12th liters? Okay, 3.7 times 10 to the 3. Well, this is kilo, so this is 3.07 kilometers. This is minus 2 grams to the minus 2, so that's centimeters. So it's 1.7 centimeters. Oh, excuse me, centigrams in this case. Again, it doesn't matter what the final unit is. You can use all of them. So this is a way to use really big and really small numbers in such a way that it's easier to say and to write. So if we look at this, 1,000 milliliters is 1 liter. 0.001 grams, another way to look at that is 10 to the minus 3. So that'd be a milligram. Okay, 10 to the minus 6. So we're talking micro. Micro is like a U. So that'd be 1 micrometer. Okay, and remember, micro is smaller, so it gets a bigger number. Okay, 10 to the 4th decimeters. That would be, a decimeter is the 10 plus 1,000. So that'd be 10 to the 4. So actually that comes out to be 1 kilometer. So can you do all of these in your head? Some of them, yes. Some of them, no. But I'm going to show you how to work through them so that you can see as they go. And we'll work some problems incorporating these as we go through. So this is the basic as to why we want to do that. So let's look at the different species before we go back to the prefixes. All right. Temperature tells the direction heat will flow. Temperature is just like water. It flows from high to low. It doesn't flow from low to high. Okay, which makes sense if you think of water. The base unit is the Kelvin, and Kelvin has the symbol K. It has no degree. We often will use the Celsius scale. This is the one you'll see around, degree C, etc. And if you use the Celsius scale, I'm going to assume that you know this next stuff. We're going to stick with this one. I'm going to go through Fahrenheit as well, because that's what most of y'all grew up with. But you'll, on banks and stuff like that where they sell the temperature, they do both. And so for Celsius, 0 is the free degree C. It's the freezing point of water, and 100 is the boiling point of water. So it's on a 10 scale, just like everything else is. Now, in Fahrenheit, which is degrees Fahrenheit, that's where if you're cooking in your oven, you cook at 350. If you cook a lot, you may have seen online recipes, European, that's becoming more common where you see things in grams instead of cups, etc. But in Fahrenheit, 32 degrees Fahrenheit is the freezing point, and 212 degrees Fahrenheit is the boiling point. We don't use the Fahrenheit scale at all. We're either going to use Celsius or degrees or Kelvin. So what is the difference? Well, if we look at it, here's our Kelvin scale, and the Kelvin scale starts at 0 and works up. The Celsius scale would have negative numbers, and the Fahrenheit scale still has negative numbers. So basically, the difference is between the Kelvin and the Celsius scale is they're both based on the 10 degree scale. But Kelvin starts at 0. There are no negative numbers, whereas Celsius has them. Now, you will be asked once to convert between Kelvin and degrees Fahrenheit. Okay? I will give you formulas for that. There are a variety of ones. I'm not sure which one is on the equation sheet. I will post, which you'll download for the exam. So you'll have that. So that's not one you have to memorize. As we go through stuff, when I say memorize it, that means you're responsible for it. Otherwise, it may appear on the equation sheet. Now, the one you are responsible for memorizing, and you do need to know the 0.15 part. Okay, that is critical for the principles class. You may have been somewhere else where they just use 273. I require the 273.15. And it will bite you later if you don't use it that way because of significant figures. More about that later. But you will be asked to do conversions between temperatures, and again, degrees C to Fahrenheit and back and forth. I will give you the equations. Okay? So if your body temperature is 99 degrees Fahrenheit, what is this in degrees C? Well, degrees C is 5/9 times Fahrenheit minus 32. So that means it's 5/9 times 99 minus 32. Keep working this. So 5/9 equals times 67, which means we get 37.222 repeating degrees C. Now, that would be your answer. Later, we're going to do significant figures. So what I'm going to do is list the significant figures off to the side. And when we actually go through it, you can go back and say, oh, that's why she got that number. So using significant figures and significant figures, or what I like to call sig figs, or SF, okay, would require you to report it in 3 significant figures, so it would be 37.2 degrees C. Okay? So that's a simple conversion there, and we're good to go on that one. So the second one says if a reaction occurs at 29.4 degrees C, what is it in K? Remember, Kelvin is 273.15 plus degrees C. So that would be 273.15 plus 29.4 degrees C, which means we get 302.55 K would be our answer. Notice when I'm done, I'm either underlining, circling, or whatever, and my unit is associated. If we're doing it in sig figs, then we will report it as 302.6 K because we would need one digit after the decimal, and we would have to round up. Liquid nitrogen boils at 77 K. What is this in degrees C? What is it in degrees Fahrenheit? There is not a conversion directly between K and degrees Fahrenheit. I'm sure somebody has one somewhere. I'm not going to give it to you, so we'll do this in two parts. So K is still 273.15 plus degrees C. We know that it's 77 K. 273.15 plus degrees C. Do you have to show all this work when you show work? No, you don't. You can truncate some. I'm going to try to show you each and every step so that there's less confusion. So degrees C comes out to be negative 196.15 degrees C. If we're using significant figures, then we will report this as negative 196 degrees C if we're using significant figures. That means that for Fahrenheit, we're at 9/5 degrees C plus 32 is our equation. So it'd be 9/5 times negative 196. Be careful not to drop the negative. So that gives us, negative 352.8 plus 32, which is negative 320.8 degrees Fahrenheit. If we're using significant figures, then we will report it as negative 321 degrees Fahrenheit. Okay? Now, here's another point I want to make. This is where partial credit rules. Most of the time, partial credit works to your favor. Occasionally, it will bite you if you don't do anything. So, for example, when you go to work this problem, if you're asked to submit work, then you need to do so. I'm going to tell you right now, most scientific calculators have to have this conversion built into it somewhere. Sometimes it's harder to find it and it's just not worth the effort. But even if you run it through the calculator, if you're expected to show work, you don't get the point for it because you didn't show work. Now, that doesn't mean you can't work it and then double check it. That's not what I'm saying. What I'm saying is when work is required, work is required. That's not optional, and I know your calculator will do a lot. Just be careful. Okay? So that was the temperature scale. The next scale is mass and weight. And mass and weight are the same, but they're different. What does that mean? Well, mass is the measurement of the amount of matter in an object. Measure of amount of matter. That's an N. Of matter in an object. We use mass and weight interchangeable because weight is the force of gravity. Exerted on an object. And so it's one of those things. On Earth, mass and weight are the same thing. But if you were to go to the moon, then your mass and your weight would not be the same. The gravity is much less, so you would have the same amount of mass, but your weight would be much less because here's where weight is. And again, we're not going to do weight in terms of figuring it out at different gravitational pulls. That's for physics. And you can have fun with the physics instructors for that one. But I just wanted to point out that they're technically not the same. However, since we're not going to the moon or Mars anytime soon that I'm aware of, that may change in the next 50 years, they are pretty much interchangeable. Okay? The standard weight is the kilogram for large objects. So when you do weight, you're talking about somebody's weight, you're talking in kilograms. Okay? But for small things like tablets, small items, then you'll use grams. Okay? And so that's actually supposed to be down here. So a lot of times we're going to use this in lab because we're going to be using things much less than a kilogram. So the gram is your base unit and it's easier to use. So the next one is the derived unit of volume is defined as the space taken up by something. And it is the cubic meter. That's the SI unit. Okay? And remember, that's centimeters cubed. Okay? So, no, that's wrong. That would be the space. That'd be the meter cubed. Centimeters are common. And down here is a cubic centimeter, but we'll get back to that one. Okay, a common unit of volume, but that's not SI, but everybody thinks it's SI because that's what we use as the liter. It has the symbol L, and by definition, a liter is a cubic decimeter. So if you look at a meter here, this is a cubic meter, and each block is a decimeter. So if you take one cube out, this is 1 milliliter. Okay? So a centimeter cubed is 1/10. Okay? And if you separate the decimeter into another 10, that's where you get the centimeters. Okay? So the milliliter, and that's the milliliter, and it's 0.001 of a liter, or 10 to the minus 3 of a liter, is also used, okay, as is the cubic centimeter. Okay, now here is a conversion that it's easy to know. You don't have to memorize it because you kind of use it a lot. And remember, 1 cubic centimeter is the same thing as 1 cc. So I like watching shows where they talk about giving somebody a shot, and somebody will say, okay, I'll give them 10 cc's. If somebody tries to give you a 10 cc shot, unless you have like rabies or something, run away, because that's a lot of volume. Okay? So I just find it interesting to watch that. Now, and you will be asked to play with utensils and stuff in your kitchen. If you cook, you probably already know this, but most teaspoons, tablespoons, etc. are now marked. There are 5 milliliters in 1 teaspoon. If you're dispensing liquid medicine to a child, it's most common, an older adult, yourself, then when you read the packaging, it'll tell you that if you need a tablespoon, then that would be 15 milliliters. And there are, because there are 3 teaspoons in a tablespoon. And so when you look at cooking utensils in your kitchen, you should find metric conversions on them now. Now, the older stuff doesn't have that. I have old cup measures that only have the English, which is, the ounces, pounds, etc. And you'll be given all those conversions. But my newer ones will have the metric as well. Now, G bottles, which I have sitting right next to me, have them as well. So this is not uncommon to see both the English and the metric conversions. So we have found out how to look at meters, liters, and volume. We're going to take it a step further into density in the next one, and then we're going to work on conversions back and forth between different units. But we are done with this section.